We're given this function f and we're told that it's defined for x greater than 1, strictly greater than 1. A good place to start would be to question the significance of this stipulation that x be strictly greater than 1. X is the upper limit on the integral, and suppose it were allowed to be equal to 1, then f of 1 would be an integral between 1 and 1, which would evaluate to 0, so that wouldn't be very interesting. The other thing to be aware of is the relationship between the limits of the integral and the terms in the integrand. Now remember, the square root of a negative number is not a real number, and we know that we're only going to be dealing with real numbers in step 1. So this expression t minus 1 over t plus 1 must be non-negative, and that's for all values of t in the range of integration, so that's for t between 1 and x. And for that to happen, x cannot be less than 1. So the purpose of this restriction on the domain seems to be so that the function is well defined and non-zero. Considerations like that are not always strictly necessary as part of a step question, though they tend to be worth making. For one thing, because they give us an opportunity to become familiar with a function or other object, and also because it is necessary occasionally to refer explicitly to them as part of the question. For part 1 then, we're asked to show that this given integral is equal to 2 times f evaluated at x over 2, and we're going to be able to do that using a substitution. Note that it won't matter whether we make the substitution into this integral or into the integral defined as f of x, because in either case we're just trying to write one in terms of the other. Now one clue here as to the substitution to use is the difference between the lower limits of integration in the two cases. So we have 2 here and 1 in the integral defined as f of x. So on that basis, a couple of obvious candidates are u equals t plus 1 and u equals 2t. Experimenting with those, we find that u equals 2t works, so substituting that into f of x. The first line here explains the substitution, the differential terms, and the limits in a little table. Now, rather than writing both integrals out straight away, it can save time and effort to make the manipulations for the integrand beforehand. So all of this implies that f of x is equal to half times the given integral, only with an upper limit of 2x rather than x. Besides plugging everything in, the only other manipulation there that's happened is that the factor of half that came along with the differential term has been taken outside the integral. Then the next line would just state that this implies the result that we're trying to show, which we see by multiplying both sides by 2 and plugging x over 2 into the function. Next, we're told to evaluate an integral in terms of f. A good place to start would be by thinking back to what we did for part 1. So for part 1, we related the given integral to the integral originally defined as f of x. Now, for part 2, we already have the integral from part 1 in terms of f of x, so we have that to play with. That means we have 2 main options. We can find a substitution to relate the integral for part 2 either to the integral in part 1 or to the integral defined as f of x. Comparing the numbers in this integral to those in the integral in part 1, it seems like that might be the best option. And you might be thinking, well, both integrals are in terms of u, so if we make a substitution in one, then we'll have one in terms of u and the other in terms of something else. But u here is just a dummy variable, which means it doesn't have any necessary relation to the final answer. We can think of it just as a label sitting on top of some underlying structure. So, in other words, it doesn't matter whether we use the letter t or u or v or anything, as long as we're integrating with respect to that variable. So bearing that in mind, the substitution u equals v minus 2 into the integral for part 2 seems to do the trick. So this is just a description of the integration procedure with the differential terms and limits. And the upshot is we get this, which is identical to the integral from part 1, only with a different upper limit. But that's okay, because we can change the upper limit by plugging a different value into the function f. So the answer is going to be given by swapping that to x for an x plus 2, and just being careful with the factor of a half. part 3, we're asked to do a similar thing again. We can expect that the numbers involved this time will be slightly more challenging. Again, the idea is to make a substitution either into this integral or into one of the previous integrals to get one in terms of the other. The way to do it is just to try a few various substitutions, preferably without writing anything initially, and don't be discouraged if they don't seem to be coming to anything. For example, one sensible thing to consider would be whether we can get this integral looking anything like the integral from part 2, with a u in the numerator and u plus 4 in the denominator. So if we were to let u equal, say, v plus 5, then we could get a v in the numerator, but we'd have v plus 6 in the denominator, and from there it would be difficult to get that into the form of the integral in part 2. One thing to be aware of is that, although a definite integral looks quite fancy, it is ultimately just a number after evaluation, and so whenever we make a valid substitution, that number doesn't change. What this implies is that we can make as many valid substitutions as we like, and they're never strictly wrong, they're only either helpful or unhelpful to some degree. The substitution we considered, u equals v plus 5, didn't seem very helpful. It didn't seem to take the integral in part 3 any closer to the form of the integral in part 2, so we should probably just forget that one, and ask instead, can we take the integral in part 3 any closer to the form of the integral in part 1? The interesting thing to notice about the integral in part 1 is that it has the same number subtracted from u in the numerator and added to u in the denominator. And thinking back to what we did for part 1, when we had two integrals of that form, we were able to express one in terms of the other. So here we can ask, can we get the integral in part 3 into that form? And considering the substitution u equals v plus 2, we see that that would give us v minus 3 in the numerator and v plus 3 in the denominator. Can we then be confident of being able to express that integral in terms of f of x? Perhaps, but it'd be better if there was some little check that we could perform before committing to writing. Consider the two integrals that we already have in the form that we're aiming for. Notice that in these two integrals, the lower limit of integration is the same as the number being subtracted in the numerator and added in the denominator. So what's the significance of this property? Well, without further reasoning, we can't be sure, but what we do know is that we can express these integrals in terms of one another and in terms of f of x. So if we could see that the substitution that we're planning for the integral in part 3 would bring about this property, then we could be slightly more confident of subsequently being able to express the integral in terms of f of x. Well, if we're letting u equal v plus 2, then that will give us a pair of 3's in the integrand, and for the lower limit of integration, when u is equal to 5, we'll have v equal to 3, and so that will give us this property of the lower limit of integration being the same as two numbers in the integrand. Again, this doesn't prove anything, it was just the first little check that came to mind, and when deciding on one of these little checks to make, the questions to ask are, is it easy enough to perform, and could it possibly make me feel more confident about what it is that I'm planning to do? So at this point, I'd be confident to start writing. The usual procedure for the substitution gives this, and now we want to put this in terms of f of x. Again, going by the lower limit of integration, the substitution v equals 3t seems like it might work, because then we'd have factors of 3 in the numerator and denominator which would cancel. So just explaining that substitution, differential terms, limits, and performing useful manipulations before writing out the integral, we get this, which is equal to 3 times f evaluated at this upper limit. There's also a nice way of doing part 3 in the official solutions, which is by defining a completely general linear substitution and substituting it in to find out what the general terms need to be. And that's worth having a look at because it's a very useful method for step. For part 4 then, same sort of thing. We have to find a substitution that will allow us to relate this integral to one of the other integrals. One thing to note is that we have 2 as the upper limit now, but that shouldn't be a problem. It'll probably just mean that we'll have to plug 2 into the function f at some point. Notice the similarity between this integral and the integral from part 2, in particular the form of the denominator. That's something that seems like it might be worth exploring. What would happen if we were to let u equal v squared in the integral from part 2? Well, we'd have v squared plus 4 in the denominator, which is what we want, and then we'd have the square root of v squared in the numerator, which is first degree, and we need a second degree numerator. But there's also the differential terms to consider. U equals v squared would give du equals 2v dv, and so we would get an extra linear term along with the differential term, and so in total we would have the correct degree in the numerator. The other thing to anticipate is, after making the substitution u equals v squared, what will the lower limit of integration be in the integral from part 2? Well, if u is equal to v squared, when u is equal to 0, v squared, and hence v will be equal to 0, and so that might be a problem because in the integral for part 4 that we're trying to evaluate, we have a lower limit of 1. Consider the following identity. We can express the integral of any function between 2 and 1 as, and this is assuming that the integral is properly defined on the intervals, which we can check that it is in our case. The integral between 2 and 0 minus the integral between 1 and 0. Now this result can best be appreciated by thinking of an integral, a definite integral, as what it is, which is an area under a curve between two limits. So this lower equation in terms of areas is essentially equivalent to the upper equation in terms of integrals. So we're going to be able to apply that to deal with this discrepancy between lower limits. One way of presenting this argument is to define the integral in part 2 as I to make it easier to refer back to. So that's what I'm going to do here. Now note that the substitution u equals v squared is ambiguous. The rule for a valid substitution is that it must be 1 to 1 on the interval, and here we have that for every value of u there are two possible values of v. So this means that we have to specify, when defining the substitution, whether v is positive or negative. For example, the upper limit of integration, when u is equal to x, we need to choose whether we're going to have v being equal to plus or minus the square root of x. And interestingly, it can be shown that it doesn't actually matter which we choose, as long as we're consistent throughout, the result will be the same. But we do need to specify the sign so that the substitution will be properly defined. This is not such a big deal, but there are two fairly easy ways to avoid the issue. The first is to use the equivalent substitution, square root of u equal to v, and then of course v must be positive. The other is to do this whole process the other way around and substitute into the integral in part 4, and then the substitution would be u squared equal to v, and so again v would be positive. So the integral looks like this after making the substitution. And there are a couple of things we can do here. We can take the constant factor outside the integral, and we can use the result that the square root of v squared is equal to the mod of v, which is the absolute value or the magnitude of v. And since we defined v as being positive, we're going to have that the mod of v is just equal to v. So we find then that this integral that we've defined as I is the integral that we're looking for, only it's multiplied by 2 and it has an upper limit of square root of x rather than x. Now we know what I is because we found it in part 2, and so we have this result then, which comes from cancelling the factors of 2 and using the fact that v is a dummy variable. Looking again at what we're trying to do, it's come down to just a matter of the limits of integration. And although that lower limit of 0 seems to be a problem, this is where we can use the result that we looked at earlier. We can get the lower limit we need by taking the difference of two integrals. So first we set the upper limit to 2 and then to 1. So to set this upper limit equal to 2, we need to set x equal to 4, and that gives f of half times 4 plus 1, which is f of 3. And then for an upper limit of 1, we need to set x equal to 1, so we have f of a half times 1 plus 1, which is f of 3 over 2. And so the difference of those two is f of 3 minus f of 3 over 2, and that's the answer. Also, if you think back to the definition of f of x, we questioned the significance of the stipulation that x be greater than 1. Here it means that the values 3 and 3 over 2 are both in the domain of f, and it's possible that there'd be a mark for mentioning that. A good way to finish off is by asking what were the main ideas behind this step question. Can we take away anything useful from it? Well, we see that we have these different integrals, and they can all be written in terms of f of x, which is itself just an integral. So if we can solve one of these integrals analytically, then we can solve the others too. But it would be a lot more interesting if we knew that we could actually solve one of those integrals. The reason that's not part of the question is probably because it involves hyperbolic functions, which are currently on the Step 3 syllabus. However, the task of evaluating f of x turns out not to be too difficult. It's something that could come up on an A-level further maths paper, for instance. One way of going about it is as follows. A couple of observations about the integral. The square root term might be awkward, because we don't have any standard integrals with that form. The t minus 1 and t plus 1 terms suggest that we might be able to use a difference of 2 squares in there somewhere. If we're going to end up with a square root either in the numerator or in the denominator, it would be preferable for it to be in the denominator. The reason that getting a numerator out of a square root can be particularly helpful is because it can allow the integral to be written as a sum of several distinct integrals. Also, lots of standard trigonometric and hyperbolic integrals have square roots and quadratic terms in the denominator. The first trick here is one that's very often useful in STEP. It's to use the fact that multiplying the integrand by 1 doesn't change it, and 1 also happens to be equal to the square root of t minus 1 divided by t minus 1. Now this does several things. It gets rid of the square root in the numerator, and the difference of 2 squares in the denominator leaves it in a useful form. Now from here, we can write this as 2 separate integrals, and these both turn out to be quite common integrals. The first is an example of an exact differential. You might study these at A-level in a topic called integration by recognition or something similar. And these come up so much in STEP that whenever you get an integral, it's almost one of the first things you should check for. The idea is just to spot that the integrand, which is t over root t squared minus 1 in this case, is the derivative of some function. That's to say, what we get when we differentiate some function. If it is, then we can think of integration as reversing or undoing that process of differentiation and giving back the original function. And in a lot of these cases, we have a square root as a denominator, and that's because differentiation takes the exponent on a square root from half to minus half, moving it from being a numerator to being a denominator. So a good question to ask when we have an unfamiliar integral with a square root in the denominator is, what would happen if we were to take that square root and all of its contents and differentiate it? And quite often the answer will be out by a constant factor, but that can easily be adjusted afterwards. However, in this case, you might like to check that we get exactly what we're looking for. And so, the first integral to be evaluated between x and 1 is root t squared minus 1. Now, for the second integral, the integrand is a standard hyperbolic derivative, and it integrates to inverse cosh t. If that means nothing to you, you may be pleased to hear that there are a lot of similarities between hyperbolic functions and trigonometric functions, including with regard to their respective derivatives. Now, as a further aside, for those who are familiar with hyperbolic functions, the official solutions give a different expression for f of x, interestingly. The first term is the same, but rather than inverse cosh of x, the second term is 2 times inverse sine of root x minus 1 over 2. And since this is a definite integral, this is not a case of 2 answers differing by a constant factor. The only way both answers can be correct is if these 2 terms are the same. So that seems like a worthwhile thing to prove. And we can do it starting from the logarithmic definition of inverse sine, then taking the factor of 2 as an exponent in the logarithm, and squaring gives an expression that can be manipulated into the form of inverse cosh. So the 2 answers are the same.